Hello everyone, I'm Mohammad Taha Khan, and in this presentation I'll be talking about functional programming in Python and its application in distributed password cracking. So I'm going to start off with an introduction to functions in Python and some of its functional capabilities. Next, I'll explain a bit about distributed or cluster-based computation. Following that, I'll give a brief outline of how passwords are stored and how cracking them is a good application of distributed functional programming. And finally, I'll show you guys a demo of how this actually works. So functions in Python are defined using the def keyword, followed by the function name and the arguments in the parentheses. Now, Python enforces indentation in functions as well as throughout the general code. Now, the return keyword allows the function to return flow back to the caller. So essentially, it's going to return to where the function was called. And Python also allows the ability to return functions within the return statements for recursion. For example, this code here calculates the Fibonacci sequence for a number, and it essentially in the return statements we're calling the function itself recursively. Functions in Python can exist without any parameters as well as without return statements. The noReturn function on the top right is a valid function in Python. Unlike C++, Python does not allow functional overloading, and the number and order of arguments cannot be used to distinguish separate functions. So essentially, every function needs to have a unique name in Python. Also, functions can take default arguments as well as out-of-order arguments. For example, in the map function here, the default value of variable b is hello. And we are also able to make out-of-order arguments call to the functions map here as long as the arguments and the variables are specified explicitly. Now, more about functions in Python. So functions in Python are essentially first-class objects. This means that they can be arguments to functions, they can be return types of functions, they can be assigned to variables, and they can also be a part of tuples and lists within Python. Now, this language also supports the lambda notation, which is extremely powerful to define anonymous functions. Now, the example code here shows how an anonymous function can be used to define the product of two numbers. And in this case, the numbers 2 and 3, and the product we get is 6. Function composition is also allowed in Python, such that the result of a function is passed as the argument to the next function. For example, the squared function right here takes a number and produces the square of that number. Now, calling the square function twice shows us that we can call the function on the result of the initial function. Function closures are also a part of Python. This allows a nested function to access the variables of the enclosed function as long as those variables are within the scope. However, the conditions for closures are as follows. So the first thing is that the nested function needs to reference the variable that is within the scope. And another added condition in Python is that the enclosing function must return the nested function when returning to the caller. Python also has built-in map, reduce, and filter functions for list manipulation. Now, these are similar to the functions that we studied in F# for class. For example, the map applies a function to all of the elements on a list. The filter filters out elements from a list based on a specific criteria, and the reduce function performs a computation on the list and produces an aggregate result. Okay, so enough with the language and the theory. Let's understand how functional programming is beneficial for distributed applications. So functional code is generic and can be extended in parallel executed in parallel on independent datasets. This becomes very handy when processing large amounts of data. The diagram below shows a scenario of distributed computation. The master passes functional code to the worker nodes that execute the code on independent datasets, and this essentially is referred as the map phase. Now, once the workers have processed the dataset, they return the results back to the master, and this is the reduce phase. So essentially, by introducing more worker nodes and passing them functional code, what we are doing here is reducing the time required to process large amounts of data. Now let's understand why password cracking is a suitable application for distributed computations. So passwords are essentially stored and transferred as hashes over the internet. So whenever they are leaked or found out by someone else, it's usually a password hash and not the clear text string. Now hashes are essentially one-way maps from password to a random string, and it is infeasible to reverse engineer a password just by looking at the hash. To go around this, attackers essentially use rainbow tables that contain millions of passwords and their hashes, and then they compare against the hashes of the passwords to actually find out what is the actual string of the password they would like to crack. Now, this can involve going through hundreds and thousands of gigabytes of data and can take an immense amount of time if done on a single machine. So processing is done in parallel by distributing the task over multiple worker machines. Now let's look at a demo to see how the use of functional programming can speed up things, and we'll do this by showing a demo of password cracking. So let me show you the code here. We have the master code, then this is the intended hash that we would like to crack against. At the same time, we have the code generates commands that would be executed independently on each of the worker node. On the worker nodes, we have the functions that essentially evaluate the hash against the complete list of files. So running the code, we see, so if I specify only a single node and run the process to crack that hash, there's only a single worker that's processing the data. The worker is running in background. And it took 15 seconds. Now, if I specify 2 worker nodes, let's see what happens. So we have 2 worker nodes, worker 0 and worker 1, and we get the password, just candy110, and the computation time, as you can see, came down to 4.4 seconds. So this is an example of how functional code can be executed on distributed systems and produce speed up results for computations. Thank you very much, and I'll be happy for your feedback.